OpenAI recently claimed their general-purpose reasoning model found a counterexample to the Erdős unit distance bound. This sounds like a massive breakthrough for artificial intelligence. But the real story is not about the discovery. It is about the massive computational gap between generating a solution and proving it is correct. By the end of this video, you will understand why current GPU and TPU architectures cannot simply verify these claims instantly, and how this exposes a fundamental limitation in how we trust AI reasoning today. The story begins with recent remarks from mathematicians including Noga Alan and W.T. Gowers. They confirmed that an internal OpenAI reasoning model generated a configuration suggesting a violation of the unit distance conjecture. The model proposed point sets where the number of unit distances exceeds n to the power of 1 plus epsilon. On the surface, this looks like a triumph of heuristic search. The model seemingly found a needle in a haystack of geometric possibilities. However, the human-verified proof relies on constructing large sets of algebraic numbers within high-degree number fields. This process is fundamentally distinct from the model's initial heuristic search. The gap between the model's output and the mathematical reality is where the true engineering challenge lies. To understand the scale of this challenge, we must look at the computational cost. The reasoning model likely performed a heuristic search to generate a candidate configuration. This step feels instant to the user. But the mathematical verification of unit distance constraints for endpoints requires n-squared distance checks. This shifts the workload from the model's sparse attention mechanism to dense, brute force tensor operations. These operations saturate GPU memory bandwidth rather than compute throughput. The hardware simply cannot process the simultaneous validation of thousands of geometric constraints efficiently. Current LLM inference architectures are optimized for autoregressive token generation, which is sequential and has low parallelism. This makes them inefficient compared to specialized C++ or CUDA solvers that utilize SIMD vectorization for distance calculations. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Here is the thing. The model's discovery relies on a different kind of logic than the verification process requires. Transformers lack native symbolic logic in their backends. This necessitates a post-generation pipeline where the AI's output must be translated into a formal proof assistant like Lean or Coq or a numerical solver. This translation incurs significant latency and introduces potential translation errors. The failure mode of relying on general-purpose reasoning models for mathematical disproofs is the hallucination of valid configurations that satisfy local constraints but fail global rigidity checks. The model might generate a set of points that looks correct locally, but when you check every single distance, the global structure collapses. This requires a brute force verification layer that effectively negates the speed advantage of the AI's initial generation step. For data engineers, this case study highlights a critical architectural trade-off between compute-bound and memory-bound workloads. While reasoning models excel at low compute pattern matching, verifying combinatorial geometry problems is a memory bandwidth bottleneck. Current TPU and GPU interconnects struggle to optimize this without specialized kernels. The existence of conflicting reports regarding Gemini's performance on similar problems highlights a knowledge gap. It remains unclear if the OpenAI counterexample is a genuine mathematical breakthrough or a hallucination requiring extensive post-hoc correction. The synthesis reveals that while AI can propose complex counterexamples, the verification bottleneck remains a purely computational, brute force challenge. Consider the specific nature of the number fields involved. The verification requires exhaustive computation of algebraic structures that current hardware handles with immense latency. The computational cost of validating these specific number field constructions likely necessitates brute force enumeration. This contrasts sharply with the model's apparent instant discovery. What appears as general-purpose reasoning often masks a hidden reliance on massive, non-differentiable search spaces that current hardware cannot optimize efficiently. The model does not actually understand the geometry in the way a mathematician does. It predicts the next token in a sequence that looks like a proof. The validation step is where the machine reality sets in. This distinction exposes a critical gap in current AI capabilities. The model reasoned to a solution, but the verification requires exhaustive computation. This suggests that the current hardware cannot optimize the dense matrix multiplications required for n-squared checks without hitting memory walls. The latency of these operations means that even if the model finds a candidate in seconds, the human team might spend days or weeks verifying it. This limits the immediate practical adoption of such models for rigorous mathematical proof without significant human intervention. The speed of the generation is irrelevant if the verification takes exponentially longer. The implications for software engineering are profound. We are building systems that generate answers faster than we can verify them. This creates a trust deficit. We cannot simply deploy these models into production environments for critical tasks because the verification layer is too slow and too brittle. The gap between the model's discovery and the mathematical proof lies in the lack of native symbolic logic. Until we bridge this gap, we must treat these models as suggestion engines rather than proof engine. The brute force verification layer is the bottleneck that defines the current state of the art. This brings us to the core realization. The AI is not reasoning in the human sense. It is performing a massive statistical search that mimics reasoning. The verification step strips away the illusion of intelligence and reveals the raw computational cost. This is the reality of current GPU and TPU architectures. They are not built for the dense, memory-intensive workloads required to validate complex combinatorial geometry. They are built for the sparse, sequential workloads of language generation. This mismatch is the defining characteristic of the current era of AI. We are pushing hardware designed for one task to solve a problem that requires a completely different approach. The path forward requires a new architectural paradigm. We need systems that integrate symbolic logic directly into the inference engine. We need hardware that can handle memory-bound verification tasks as efficiently as compute-bound generation tasks. Until then, the gap between discovery and verification will remain. The AI will propose and the human will disprove, or the human will spend weeks proving the AI right. This is the current reality of mathematical discovery in the age of large language models. The technology is advancing, but the fundamental constraints of silicon and memory remain. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.